Hi guys, in this short lecture we're going to talk about how Poisson's equation and Laplace's equation can be used to solve for the voltage directly from the charge distribution. And we're not going to do a lot of examples of solving problems this way, just because like solving any differential equation, solving a second order differential equation requires a little bit more intuition than actual technique. But it's important to know about these equations because they certainly are commonly used to solve for the voltage. And then, of course, once you have the voltage or the potential, you can use that to solve for the electric field. And often you can easily solve Laplace's or Poisson's equation using computational techniques if you can't do it using the old school differential equation techniques. The whole point of these equations is basically we want to go ahead and skip the electric field, which is a vector field and is more complicated than our scalar potential field. And we're going to instead relate the potential directly to the charge distribution. Okay, so let's start with this equation here, relating our electric field to the potential V. Okay, we also know, right, that the divergence of our electric field is equal to the charge density rho over epsilon naught. Okay, so we're basically going to combine these two equations, and I'm going to take the divergence of the negative gradient, okay, of our potential. And that, right, basically all I'm doing is substituting this in for E. So that has to be equal to our, charge density over epsilon naught. What you're doing here on the left-hand side is taking the divergence, right, the divergence here of a vector, which is what you get when you take the gradient of the potential. So if you remember this dot product of our del operator and our gradient, we're going to end up with a scalar. Okay, so what results out of this is a scalar, basically the del operator squared, but now it's a scalar. So this is a second order partial derivative of the potential, and that's going to be equal to the charge density over epsilon naught. And this is what's known as Poisson's equation. Okay, so that's an important one. Okay, just a little background and what's going on here. This guy is known as the Laplacian. You can see it in different forms in Cartesian, cylindrical, and spherical in the back of the book. But in Cartesian, I can write it out. It's going to just be again, it's a partial derivative, but it's a second order partial derivative in each of our directions. Okay, so that means that if I take the second order, or if I take the Laplacian of the potential, I end up getting this here. Okay, and this right here is a second order differential equation that we have lots of mathematical techniques to solve. Okay, so we have a special situation when rho is equal to 0, which means no charge in the area. Okay, that means that the right-hand side is going to be equal to 0. And this is what's called Laplace's equation. It's really just a special form of Poisson's equation, where rho is equal to 0, but it gets its own name because you can use some different techniques to solve it when the right-hand side is equal to 0. Okay, but it's also important to note when we're looking at Poisson's equation that rho equals 0, okay, it does not mean that V equals 0, okay? The potential does not necessarily equal 0 because, right, we're taking the second derivative of the potential and that's what's equal to 0, okay? It also doesn't mean that the electric field is equal to 0, okay, at that particular region in space, okay? It just says something about their gradients.